is a leader of the group of quantum optics and quantum information at the Bogolubov Institute for Theoretical Physics here in this institute. And Professor Semenov is the leader of this field of research in Ukraine and also is recognized in the world. So it's a big pleasure for me to introduce Andrii, please. And the title of the lecture is Quantum Measurements. Quantum Measurements. So, Andrii, please.
Thank you very much, Saki, for such nice introduction. Let's just check. Everything works. Okay, yeah, thank you very much. I'm Andrii Semenov, as it was introduced already. I'm doing quantum research, working in this institute. So I welcome all of you here in Kiev. I welcome our online audience, which is also very nice to see you from the world around. I see that we have really a broad audience now from many, many countries. Believe me, now we are, I hope, very widely broadcasted. And just a few words that I would like to know about my audience today. Please rise. I understand that most of the students are physics students here in this audience, yeah? Who from you is not physics? Okay, 1, 2, 3, yeah? Okay, I see. And do we have online? Do we have rising hands? Do we have such students? Not physics students. Oh, we do not see.
Yes,
we have a little bit. And do we have students who didn't study quantum mechanics so far? So, yeah, but a little bit. Yeah, okay, I see. My task here is to give you very short introduction to quantum physics. This is really difficult task that I have now because I should tell you about things that students usually study during the semester. Of course, it's impossible to do during my 3 hours, yeah? So you can ask me questions. Please raise hand, interrupt me anytime when this is short question and you do not understand something. Simply raise hand. The same is online, please. So, and Mikhailo, who is assisting me today, will help me with online student when there is a short question. But my lecture will be divided in 3 parts. And after each part, I will give some small break. We will have a possibility to ask me questions. After that, we will have small coffee breaks, yeah, and we will go future. Okay, we would like here to study about quantum sensing and quantum metrology. I would like to tell you about a little bit about quantum metrology, what you should know about this technology, about this field of science. Actually, in order to understand it, you should study 2 different branches of researches. Quantum physics, this is what you should know, and another one, classical estimation theory. So without these 2 branches, it's very difficult to understand what quantum metrology is dealing with, yeah? And quantum physics, I will give you now lectures. This will not be the whole course of quantum physics. Believe me, it's impossible simply in 3 hours, yeah? Only very, very comprehensive thing you should know. And after that, today, after lunch, you will have lectures from Professor Andrii on totally different topics about classical estimation theory. And tomorrow, you will have a lot of fun because you will have a lecture from a very famous physicist from the University of Nottingham in the United Kingdom, Professor Gerard Zadesa. He will combine these 2 topics and will talk to you about quantum metrology. Okay, and now we are going to quantum physics. Okay, a little bit checklist. Please write yourself, make notes, what you should know from my lectures. First of all, you should understand, this is what you should understand from my lectures. If you do not understand something, please ask me anytime. What is quantum states? Pure and mixed. Another one, what is quantum observables? Quantity which we can directly measure, okay? Quantum measurements, you should very good understand what is so-called Born's rule. This is something that has been invented more than, a little bit less than 100 years ago. This year, you know, we're celebrating 100 years of quantum mechanics. This was 2 famous equations because quantum mechanics was invented 2 times. First time it was Professor Heisenberg, yeah, Werner Heisenberg, and another one, Schrödinger, yeah. But in order to connect their equations with reality, one needs to understand what is measurement, what we see in experiment. And this is Born's rule. This is what you should understand. Very important things in this connection, very important notions that you should know and that requires for your understanding, so-called positive operator valued measure. This you should learn from my lecture, okay? Time evolution, concept of Hamiltonian. This is not really important for quantum metrology, but also used. So you should at least a little bit understand. But if you studied quantum mechanics, you already have this knowledge, okay? And last but not least, you should clearly understand between two very different concepts: measurements and estimations. Okay? This is really different things. Okay? Okay, let's start. And this looks a little bit strange, but I will start actually with classical physics. Why? Because classical physics is something intuitive. You understand this intuitively. And after that, we will try to cross this border between classical and quantum world, okay? Having this knowledge. Okay, first my question to the audience. There is such a notion of state, classical state. How do you think? What is it? For example, we have one-dimensional particle. In the audience, what I say, state, classical state of the system. Yeah?
Point in the phase space. So
yeah, exactly. Coordinate and momentum, yeah. Position and momentum, yeah. When this is what, so just two numbers when this is 1D particle, but yeah, one single dimensional particle. For example, harmonic oscillator. When this is more than 1D, of course, this you should multiply it with dimension. So, okay. Position Q and momentum P. Just two numbers in 1D case. For example, this can be a harmonic oscillator, yeah? For not physicists, maybe this is very strange equations, but I will try to explain here, yeah, that everything is described here with classical Hamiltonian or Hamilton function. I simply consider dimensionless units. So my mass is 1, my frequency is omega, and so on, okay? So this Hamiltonian function is function from position and momentum. This is energy, actually. P square over 2 plus Q square over 2, okay? This is simply a harmonic oscillator. And there are two equations from Hamiltonian. We can get two equations of motion. We can solve this equation of motions, and we know time evolution already, classical time evolution. And this is point, this is how harmonic oscillator behaves. So this is point in phase space. This simply will rotate around this circle. Each time you have another state of classical system, okay? I believe this is clear for you. What is this concept of state? This is already very important. Believe me, if you now understand this, you will understand after that many other things. But we may have another system. For example, electromagnetic field. The whole electromagnetic field is a very difficult concept. And I will talk about not the whole electromagnetic field, but about one mode of electromagnetic field. For example, only with one wave vectors. So plane wave distributed in one direction, okay? Here we have such complex dimensionless number, alpha, which calls complex amplitude. Even if you are not familiar with classical electrodynamics, it should be intuitively clear for you what is it. Complex amplitude, this is in front of F step in E Chi-R, and this is also will behave something harmonically. Because you have complex number, you can separate it on real and imaginary parts. And this is also some analogy to position and momentum. But this is not really physical position and momentum. This is position and momentum, this is like electrical and magnetic fields. And in quantum optics, we usually use such a word, such a terminology, field quadratures, for this very strange position and momentum. All people in field theory, I see here colleagues from the field theory, they sometimes use field position and field coordinate and momentum. Okay? So, we understand what is pure quantum state. But I have such a question for you. What if you do not have complete information about your position and momentum? Yeah, in real situation, this can be, for example, in this room, there are a lot of molecules, and you want to know, for example, position and momentum of each molecules. It's impossible to know. But also this one can imagine this only for 1 degree of freedom, at least theoretically, and in quantum optics, this is very typical situation, even simply in optics when we have single mode. Mixed quantum states, when you have no exact information about Q and P. How so? Pure quantum states, we have full information about this point. Mixed quantum states, we have no exact information. How to describe, in this case, state of the system? How do you think? What to do in this case? Probability distribution, yeah. Probability distribution, and probability distribution give you state, mixed state of classical system. For probability distribution, there are two properties. First, this is probability distribution. This should be positive definite, yeah? It cannot be negative, it's clear. And it should be normalized in 1. This is very clear things, yeah? One example is very known. In quantum optics, we call it thermal states. In statistical physics, people use another terminology, but because I'm a guy from quantum optics, I will use this one. Thermal states, when rho from Q and P, it doesn't depend on time, it's possible. So so-called stationary states. 1 over Z is some normalization constant, yeah? And this is exponent minus HQP Hamiltonian divided by K Boltzmann constant, and T is temperature. Yeah, this is just an example of thermal state. Okay, example of mixed state. Okay, we understand now very important concept. What is state, not quantum state, sorry, classical state, yeah? What is state in classical physics? Another important concept is observable. Observable, this is a quantity that we can measure, directly measure, yeah? Let's think about examples. Could you please tell me what you can directly measure, for example, for a 1D particle? Position, can you measure? Yeah, you can. Momentum, energy, of course. So, example, QP, HQP, and actually, any function A from position and momentum is called observable, classical observable. Actually, this term is from quantum mechanics. I simply adopted it here, yeah? So, this is from quantum theory, but this will be very important for us. And now I have one very interesting question to the audience. Could you please tell me, temperature T, is it observable or not? Yeah, louder. Depends on system. Okay, okay, one particle, this one particle, T is observable in this concept, for this concept. Look how T is defined.
Just like measure over reservoir in which the system forms.
Measure, yeah. And this is parameter, yeah? Parameter characterizing your classical state, okay? Temperature cannot be directly measured. This sounds very strange for people outside, for example, quantum sites. This also, because when you have, for example, I don't know, fever, you go to medical doctors and say, have you measured your temperature, yeah? Next time you should say, doctor, temperature cannot be measured, yeah? Temperature should be estimated, to be honest, yeah? So this is parameter and temperature estimated. Technically saying, you should provide many measurement on some physical quantities, for example, energy, and on this basis to estimate temperature. Simply in standard situation, because ergodicity averaging in time is the same as averaging with ensemble. So this is the same as averaging with many similar prepared systems, okay? But this is very important. So this is very easy thing, but you should understand it's very, very clear, this difference between measurement, even in classical physics, and parameter estimation. I believe it's clear for you, to you, okay? Temperature is an example of a quantity, physical quantity, which cannot be. Some questions for you, for example, for audience I have. Angular momentum, is it observable or not?
Yeah, just because it's functional.
Yeah, mass of a particle. It's parameter. Yeah, it's parameter, but very interesting question, because sometimes some people from Foundation of Physics may disagree with you. Yeah, but this is already, but in our non-relativistic quantum mechanics, this is parameter. Okay. And now very provocative question, just think about it, another quantity. You should think it, and after that, after my lecture, we will discuss it. Velocity. Yeah, what is velocity in this concept? Yeah, you don't have. So here we have Hamilton formulas. Here in Q and P, we don't have velocity here. Think about it, and we can discuss it after that. Okay.
Andrii, we could consider temperature as total energy divided by number of particles.
Average energy.
Total energy.
Total energy, but average still. Yeah, because it's also fluctuate.
I mean that there is energy conservation.
Oh, but then this is not temperature. Then this is energy. Yeah, then this is energy. Yeah, in this case, but in this case, you have already a lot of information. Okay, let's discuss a little bit later, because I will not be in time with my lecture. Okay, I have a lot of questions. So, what we now have, we now can introduce with you a very important concept of expected value of observables. Yeah, expected value of observable A is simply such an integral. This is simple averaging, and I believe it's clear to you. Yeah, but we are interested. This is only very, very small information about our observable, about our state, about our classical state. More generally, what we need, and now I will present you very important equation. We need information about probability distribution of this observable, because if you provide many times measurement with different systems which are prepared in the same state, each time you will get different values of this observable A. Okay? And as a result, you need probability distribution for this observable. And I believe this equation is more or less intuitively clear. That this probability distribution, please understand, so I would like to point your attention that here P from A can be or discrete or continuous variable system. So when this is discrete variable, this is probability. When this is continuous variable, this is probability density, okay? I simply use here the same. Integration O, here is mistake, C, no, R square with from minus infinity to plus infinity, okay? Rho from QP, and here is delta function. I believe you're already familiar with the concept of delta function, yeah? It's something like cut, yeah? You just value from here. And A minus A from Q and P. So this simply gives you this probability distribution from the A. I believe this is really clear. If it's unclear to you, please raise your hand and ask me now. Okay, online? Everything okay. And this function, sometimes in classical theory, is called this delta function as response function. Response function of your measurement device. Do we have here some people from experiment? Only theoreticians? We have. We have Professor Kardyuk. And Professor Kardyuk can tell me now that, Andrei, I'm sorry, but I never have perfect device, yeah? So it doesn't work. Okay, you have no broken state, this I can believe, but perfect device never exists. And I agree. Perfect device, in principle, does not, devices do not agree in the nature. It's impossible. Nobody has seen it, except of one devices in quantum optics, which one uses recently. So transition edge sensors. Experimental, my colleagues try to convince me that they're perfect. I still do not believe it, but okay. What does it mean that device is imperfect? This means that we should have not delta function. Delta function, this is very sharp peak, yeah? But this will be already something wider. And your response function will be like this. And ladies and gentlemen, what I would like to tell you, this equation is very, very important thing. You should write it to you, because what we will have in quantum world, what we will have in quantum in quantum mechanics, it's full analogy, which is called Born's rule. And simply this is full analogy for this equation. Okay.
We have a question from chat. Sorry.
Yeah, Anton, please, I can.
So, Aditya Kumar asking, what about phase of the wave function phi? Is it a valid operator or observable?
Very good question. Thank you very much. Super question. But this question is related already to quantum mechanics, because phase of wave function. Now I'm thinking, so now I'm telling about quantum classical things, yeah, but also in classical things, when this is harmonic oscillator, it has phase, yeah, simply angle on this circle, okay? Phase, in principle, is also a parameter. People have trying in quantum mechanics have found a concept how to explain phase as observable. This was more or less unsuccessful. But when we consider it as a parameter, we can estimate it. And this is a typical task for quantum metrology. But we will talk about this question. Thank you very much. Very important question, but we will talk about it a little bit later. It's also example of parameter. Okay, another question online, Anton?
No.
No. Okay. Let's talk about it. So what is properties? So more technically, what are properties of this response function? Response function, so it's a function which, first of all, is positive definite, because this is probability distribution again, yeah? And this should be normalized. Normalized with A in all domain of its validity, okay? It should be integrated. And so when this is discrete, it should be simply sum, not integration, but sum. And if I, as a theoretician, has found such a function, such set or such a function or this thing, so I can tell, should exist experimental procedure how to measure it. Maybe experimentalists never can implement it, because this will be very difficult, but it should exist. But when experimental people tell you that, okay, I have a measurement, direct measurement procedure, as a theoretician, I should say, okay, there is such a response function for your device. This is very important. Okay. Now, ladies and gentlemen, we are almost on the border of class.
Just a question.
Yeah.
So each device has own response function.
Yeah. Yes. Even more. Device, not device, but measurement procedure may have, because you may change measurement procedure on your device. And this will be totally different response function.
complex.
Yeah. This is very, yeah. This is what I would like to tell you, that today in quantum science and technology, this is very important task of theoreticians, not only to solve equations of motion, okay? But this is also an important task to find this response function or its analogy in quantum world. But like I said, we already here, this now should cross border with quantum world. Let's check if you understand everything, okay? First of all, pure classical state. I believe it's clear to you, yeah? Point Q and P. Mixed classical state, okay? Probability distribution function. Classical observables. Any function from Q and P. It can be not single function. It can be a lot of different functions, okay? So it can be a set of functions, like a vector, for example, yeah? Q and P together is also an observable. This measurement rule, analogy of Born's rule, which looking like this. And last but not least, you should understand that classical mechanics include time evolution. What I would like before, we are now staying, like here is something like checkpoint, okay? So our next step is simply in quantum world. And before going there, I would like to check with you last things and to consider you some things that can be a little bit different in classical and quantum world. Look here, pure classical state itself because is also an observable, because Q and P also as a pair in classical physics, they are observable, you can measure it, okay? So this is our state, so state in classical physics is also an observable. This is intuitively clear. And this picture to you is now can be intuitively clear. And now when we cross board, we will lose this intuition because now I will say about something that totally non-intuitive. Just think it's such so. Change your mind a little bit, okay? Change your mind here before this border, yeah? That state and observable consider that this is some, I don't know, some concepts that are not physical, that they are not intuitive, yeah? Some, how to say this word, I forget, so this not intuitive concepts, so abstract, some abstract concepts. So you have some state of the system, you have some observable which your apparatus device can measure, and only with this rule you can understand what you have in experiment. Of course, in classical words, it sounds a little bit strange because you clearly understand what is it. Okay? So this is end of my first very short part of my lecture. I'm ready to answer your questions, if you have, because now we crossing border.
Yeah, just a small message for online participants. So please raise your hand if you want to ask a question or just write them in the chat. Yeah, thanks.
So maybe somebody wants to
from Zoom. Okay.
These response functions and how can we obtain a response function? I mean, what I want to ask is, so we have observables and we have parameters, and we have this response function, and we have to obtain it somehow. We can obtain it by theoretical calculations, or we can obtain it from somehow measuring or estimating it in the real world. But how can we measure or estimate it if we don't know the response function of the measurement apparatus we are using?
Thank you very much. Thank you very much. Very nice question. Yeah, first of all, I would like to say both, actually saying. It's possible to do theoretically, yeah? Maybe how to do it theoretically, it's easier to explain. It's a little bit surprising, but in quantum world, okay? In classical mechanics, you should consider formally, you should consider equations of motion, system plus your apparatus. You should solve it. After that, you should understand what exactly you measure. So this is a really complicated procedure. It's not easy procedure. In quantum mechanics, very similar things. But in quantum physics, there exists such a procedure, like also in quantum optics, for example, like it calls detector tomography. Detector tomography is really interesting things because with some suggestions that you can measure some observables, yeah? Typically, this is some combination of Q and P, but can be another one, yeah? You can reconstruct this function. This will not be a response function. In quantum mechanics, actually, I would say, this calls positive operator value measure, okay? But here, you can do it. Yeah, so you can do it, but this is, actually my answer is both. Both procedures works. But theoretical task in this case is not really easy. I even don't touch it. So, okay, let's...
Okay. Other questions, please? Dear students, please ask. You have such opportunity. Okay.
Yeah, Yura?
Yes, I would like to get back to the problem of temperature for a minute. You've mentioned that, well, the only time you've mentioned temperature was in the mixed state. That's the only place where we've seen it explicitly. And it seems that the temperature here is a parameter because it is not included into Hamiltonian. And thus, this temperature is not about energy, either full or not full, but more about the information properties of the state, how much information we have about the state, and it is by no means linked to the actual energy of the system, right? Am I right?
Yeah, you're right. Because temperature is actually, from thermodynamics. And from this also, temperature is related to another thermodynamical things, which calls entropy.
Mm-hmm.
Yeah, okay. And this is also possible to connect all these two parameters. And this is actually a parameter. This is characterized. So entropy, can you measure entropy?
I don't think you can measure it.
You can't. Yeah, you can estimate it, actually.
So what my question was about the procedure. How can one realize that some parameter is actually a parameter, or it is something we can measure? Well, if it is not included into Hamiltonian.
Are you asking me as an experimentalist or as a theoretician?
I'm not sure. Which would be better?
You're not sure. No, because it's a very important question, Yura. Because if you're a theoretician, you should clearly understand that if your physical observable is function of Q and P, this can be directly measured. Okay?
All right.
Actually, we can also, I will not tell you now about this, but this can be directly measured, But when this is parameter, which is in your distribution function, rho from QP, sometimes people call it a Liouville function, When this is parameter which appears there, this is simply parameter, which should be estimated.
Okay.
You will see during the school this many times, I promise you this. And you will understand. I am very sorry that I do not stop on some physical things now, but because I would like to have such a content.
Thank you very much.
Okay, thank you very much.
Thank you. So, are there any other questions?
Yes, we have another question from chat. So you mentioned about the measurement rule. I'm just curious to know that what happened when we will major in different phase, and that phase will belong to classical as well as quantum. How could we distinguish it?
Just a moment. About phase, I promised you we will talk a little bit later, and about quantum thing also. At the moment, I would like to, so at this part of my talk, I would like to concentrate, let me concentrate only on classical things, okay? Yeah, and what is quantum phase? I have not told so far, but maybe, so for the students, I will be happy to discuss it after my talk, even after my lecture. And in the lecture of Gerardo Odessa, I believe he will also mention this thing. So let me postpone answer your question, okay? Because this is a little bit, so we should understand a little bit more. Okay, ladies and gentlemen, I believe We are now ready for crossing board. Everybody ready, yeah? So can we go? So you have prepared your tickets, your travel passports, because now we're crossing board and we're going to the incredible, strange, wired quantum world. I'm your guide here. Okay? So, welcome on another side. We are here, just on the border. It's not too late to return back, okay? First very strange thing that we have from here, that pure quantum state is not an observable anymore. You cannot measure it. As it was in classical physics, Q and P you can measure. Here, pure quantum state is something very, very different, and you cannot measure. It's even not position and momentum for particle. What is it? This is pure quantum state is a vector, for which we have such a symbol which calls psi, can be any letter, and after that such a bracket. It calls ket vector, okay? In abstract Hilbert space. And this is really strange vector, because first of all, never think that this is a vector in 3D physical space. No, it's not. It's not like this psi vector, okay, with arrow. This is vector in some abstract Hilbert space. This is not our physical space, okay? In this, depending on the system, so this is even not 4-dimensional like space-time, if you're familiar with special relativity or general relativity. Dimension of this vector, of this Hilbert space, can be different for different systems. It can be finite dimensional, it can be infinite dimensional, okay? Depending on the physical system. Another strange things, coordinates of this vector, yeah, components, can be complex numbers. Absolutely unclear what is it, yeah? So complex number, and last but not least, we are interested only in such vectors who has unit length. So scalar product, which is written like this, and I will tell you a little bit more about my color scheme here, is equal 1. To be honest, actually saying, I should not consider this like this. I should say you a little bit different things. I should tell you that there is this vector is defined up to one constant. Yeah. Physically, for us, it's interesting only to normalize it. So sometimes people in quantum field theory, please correct me, QFT people, if I'm wrong, call it as a ray. Yes, rays in Gibral space. Yeah, so this is a set of vectors which difference only with their length, collinear vectors. Okay, this is first very, very strange things. Do not see now any physics, please. Here, no physics here. It's abstract concepts, okay? We can, so you can not measure it, but I believe nobody hear me. We can estimate it, or better to say, reconstruct this thing, okay? But no direct measurement. So this is just something very abstract. And now what I should tell you, to give you some information, what I should tell you, because not all students here are familiar with quantum physics. I understand that my lecture is very, very simple for people who is familiar with quantum physics, but I should give for broader studentship, so this concept. Let's consider this terminology and all these things, how they are working in quantum physics. There is English word, bracket. Okay? Or Dirk, simply put this word in two parts, bra and cat. And cat, this is something that right-hand sided. Okay? Cat vector is psi, is written like this. Here is just an example that this vector has, for example, in some bases 0 and 1, each vector has its own basis, okay? You always can choose bases for vectors, yeah? And in this Hilbert space, it's also. I simply choose some basis, see that coordinates are C0 and C1, and this is vector column. It's not necessary to have two dimensions. It's simply I do not want to write in my presentation a lot of, yeah? 10, for example, dimensional, yeah? Or infinite dimensional. It's just an example to understand. Okay? Bra vector, when you transpose it, okay? And complex conjugate. And this is, so, looks like this. This is first part of this bra. And this is another vector. I simply said this was vector psi. This vector phi, let's consider simply another vector. And this will be D0 conjugated, D1 conjugated, because this was D0, D1 column. Okay, bra vector. Mathematicians, when we have among you mathematicians, mathematics students, mathematicians, they can tell me that bra vector is actually a functional. What is functional? This is something that wants to join ket vector. This machine, she looks for ket vectors. Where is ket vectors? I take ket vector, and after that, give as a response a number. And this number is called scalar product. Okay? So for each ket vector, you always have bra vector. It's clear. Okay? So this is simply when you need to write scalar product, and this looks like this. We write this in such form. You see psi, phi, psi is simply D0 conjugated, C0, D1 conjugated, C1. But this is not only single product that exists between these two vectors. There is another kind of products. How do you think? What we can do more? From linear algebra, I believe you're familiar with linear algebra. What we can do more? Yeah. It calls dyadic product. Okay? When you column multiply with row. In this case, so it looks like this. This is actually generalized projector, it calls. Okay? And what you have such a matrix. Yeah. Result is a matrix, or we call it operator. Why operator? Because this matrix can be multiplied with ket vectors, and we can get ket vectors again. Okay? It's clear. So, do we have some questions here?
We actually have a question for a previous topic about the response function. It's fine.
Anton, can we move this a little bit to another, to maybe to to coffee break when we before coffee break? So because with all respect, simply to keep the time.
Sure.
Okay, so I will be happy to answer your question. So this is not a problem. Simply to follow this. I mean about this point. And maybe when I talk about quantum analogy of response functions, so you can understand it even better, you will reply a question. With this bracket formalism, yeah?
It's like... First of all, sorry for my bad English.
No.
Dyadic products, it's like a vector multiply.
Dyadic product is simply analogy dyadic products.
But we have in end and the tensor.
Yeah.
Thanks.
It's like we say operator here, okay? So you can say, of course, tensor, yeah?
But this is simpler.
Yeah, okay, but we have here so terminologies that we can use, yeah? Better not to use
this. I don't understand when our Nam studied it. Why we don't call it tensor?
Why you don't understand. But okay, in different branches of research, there are sometimes different. But actually, yes, you're totally right. Like a tensor product, yeah.
I think it will be called like outer product. So scalar product will be the inner product and the outer product in this case.
Inner product and outer product, yeah, exactly. So let's go forward. So we understood what is pure quantum state. Let me check time. We understood what is it. Okay. The next point we should understand is what is observable. Okay? What is observable? And observable in this case is also an abstract concept. Because in quantum physics, observable is a matrix or operator. And this sounds very strange because in quantum physics, in classical physics, you had function from Q and P. It was some number, I can understand, it has some value, yeah? Which value may have matrix. So, to be honest, this is not simply operator. This is operator, should be Hermitian operator. I believe you know what is Hermitian matrix, Hermitian operator, yeah? So you understand this concept. I believe, if not, we can also discuss it later. So analog in classical words, this is real functions, okay? This analogy, but we can discuss it later, what is Hermitian, if you need, but I believe that people who studied linear algebra are already familiar with this. No numbers here, observable. If it's observable, it should be some numbers. So my measurement device should show something. What it can show. Matrix.
All vectors.
Eigenvectors. Eigenvectors, yeah, eigenvectors. Eigenvectors, eigenstates, we say, yeah. What is eigenstates? This is solution, eigenstates and eigenvalues. So we have such an equation, operator A acting on vector an should be an number, an. And eigenvalue problem is to find such vectors and numbers which satisfy this equation. This was in linear algebra. Oh, it's already something, yeah? Yeah, this is already something. This is already something. We can suppose that what we will measure is eigenvalues of this operator. Okay? Well, some math that you may study in quantum mechanics can simply show you. It turns out that different eigenvalues, they are orthogonal. There are some interesting exceptions, but okay, they are orthogonal normally. There is completeness relation. This means that if you take some vector, yeah, arbitrary vector psi, some state, you can always expand in such series. This will be some psi n, and this psi n can be found as a scalar product, an with psi. Because this is the basis, this relation, so you can expand some these things, yeah. So any vector here, and your coordinates looks like this. Look here what we have. This is coordinates actually in some basis. But what's this basis correspond to? To an observable. Observable, I consider it observable, gives you a basis, yeah, where your state has some coordinates. In quantum physics, we say representations. So quantum state can be considered as a vector, can be considered in different bases. What means basis? Basis is given by an observable. You choose observable, experimentalist told me, I have such an apparatus. Okay, ideal, perfect, sorry, apparatus, yeah, at the moment. I tell, okay, I will look what is basis for this apparatus. And I have coordinates in this basis. My state has coordinates. And after that, we will go to the next important things, which is called Born's rule. Born's rule, it was invented in 1926 by Max Born. Yeah, very interesting how this appears. And this is actually one of the postulates of quantum mechanics, very similar to Schrödinger equation, very similar to everything to Heisenberg picture. Yeah, this is also very important things. And what it's postulated here? First, possible measurements outcomes. This is AN, eigenvalues of an observables you measure. Okay? These are possible measurements outcome. Even for the pure state, when it seems that you have total information about quantum mechanics, you may have non-deterministic value of this observable. Not for all cases, but you may provide experiment many times, and you will have different values, even for pure state, even for pure quantum state. And Max Born postulated, and it was checked already many times with a lot of science after comma, that this is simply, this probability P from AN is simply a modular quadrat of this amplitude or this scalar product. And this is already connection of abstract concept of psi function, yeah, of quantum state and observable with realistic world. I understand this is so far not really realistic because we do not have now experimental and these disadvantages. Yeah, we will have it, I promise you. Yeah, but nevertheless, it already gives you answer on this very important question. So this connects two words of abstract mathematics and the word of physics. Okay, this is what I called analogy to this, what I called measurement rule in quantum classical physics. I wrote you measurement rule and this integral. You remember, yes? Just a few minutes ago. And now I have this one. Okay, now I see that I should give some, answer some questions. Yeah, maybe, or, okay, let's go beyond, and after that we will have a small break, okay? Just one slide more, and after that we can make a small break. A few examples. And first example, which is well known and which many people use, is position operator. When your operator A is Q, simply position. In this case, we have very interesting thing because spectrum of this is continuums. Yeah. So this means, so we can solve this eigenvalue problem, but these scalar products, this will be not Kronecker delta symbol, but delta function already, because this is continuous spectrum. Okay. So this is not discrete. Okay. In this case, we can expand psi, this state, like integral, the Q, psi from Q, Q, and psi from Q is simply such a Q, psi, scalar product, and this is called in Schrödinger wave mechanic like wave function. Yeah, this is wave function. This is actually what quantum mechanics started. Yeah, not exactly, because first was Heisenberg representation, that in 3 months, I believe, or a little bit more, we'll celebrate 100 years. Schrödinger equation appears, and this appears a little bit later for equations, but the concepts of wave functions, this is de Broglie, I believe, yeah, and it was even earlier. Okay, and probability distribution, but in this case, this is continuous variable, so this is density probability, is simply module square of this. Sometimes people call it as this psi from Q, a wave function, but also probability amplitude, but this is probability distribution. Yeah, this is Born's rule. This is original Born's rule. Born originally has written these things. I don't know if it's true, but I heard such a story that when Born submitted his paper first, he has made a mistake because it rules was without this square. And only in the proof, he decided to put square here. It was corrected. Yeah? Because without square, it would be incorrect. I don't know if it's true again, but maybe one should speak with historic people who is interested in history of physics, so more exactly. But I have heard such a history. Another story. Yeah, yeah, of course. No, this should be very well known. Folks, I simply don't know if it's really true. Okay, Hamiltonian. When A is H, this is energy. I would like to measure energy. In this case, energy can also have continuous spectra, but more interesting things when you have something like a harmonic oscillator, and this has discrete spectrum. Yeah. You have also Schrödinger and related equation is called time-independent Schrödinger equation. This you know maybe, yeah? That eigenvalue equation for the Hamiltonian is time-independent Schrödinger equation. And in this case, you have eigenstates of energy and possible values of energy. In energy representation, you can expand it in series, not a problem. Again, you have Cn, probability amplitude for the energy. And P from En, which is modulo square of this probability amplitude or this is simply probability to absorb such energy when you measure energy. Okay? I don't know if coffee break is already prepared.
Yes.
Yes. So I maybe now stop a little bit and I can answer your questions now. Okay, and after that we will have coffee break, maybe for 10 minutes. Yeah, and after that we will have one more coffee break during my. Okay, questions. Yeah.
Due to Born's rule, from quantum measurements, we can obtain AN, but psi function in that case, it's work like T in classical mechanics. It's like looks like parameters that we can't just measure or.
Very good question. Thank you very much, by the way. Yeah. Let's go back to our classical world. Like we can do it in our virtual journey. Yeah, very easy. This is like this, rho from QP. But very unusual. Yeah, very unusual. Because psi is only from Q. Yeah. And this is rho from QP. I will explain you how to, in a third part of my lecture, I will explain you how to generalize it.
So
Yeah.
function they also can measure.
Cannot be measured.
Cannot be measured.
Yeah, because this is okay in classical physics. This is Q and P in principle measurable. Yeah, so like together in classical physics, together Q and P in classical physics you can measure in classical. Yeah, not in quantum. Quantum not of course. Yeah, yeah. Rho from QP, This is already something that you should do this measurement many times with similarly prepared systems, and after that you can reconstruct it. Okay, you can also use here word estimate. But for this case, people usually word reconstruct. In quantum states, so this psi function, when not psi function, but density operator, I will tell about it a little bit later, it calls quantum state reconstruction, this procedure. It exists. But not directly measured.
Other questions?
Maybe small addition about the Born's rule. So
Okay.
if I remember correctly, that historical note, I saw the paper. It's the square appears like in a footnote below in the paper. I've like seen it. It's like it's like he's like. I think in the paper he says that the probability is proportional to the wave function, and then there's a footnote, and in the bottom it's like upon like more careful consideration, it can be shown that it's the square.
Okay,
like
thank
that.
you very much. I didn't know this.
Okay, this is comment question.
Yes, Sasha.
Is time an observable?
No. Very philosophical, very good question, Sasha. It's not an observable. But this is also not a parameter, like in this sense, like I said, because time, this is time evolution. In principle, very good question, because when you consider psi function and when you consider time evolution, you have integration with the q, but not with t. Actually, when you consider your rho from q and t, this should be told when we will be very formal from the probability theory. We should say probability distribution to get momentum q under condition that time has value t. So this is like conditional. So this is like a parameter in this case. But what does it mean, this parameter? When you measure this, when you decide to measure it, there is another concept in quantum physics very interesting, time of arrival. Not really familiar with all recent advances in this case, but in 1D case, this can be considered, this time of arrival can be considered really as an observable. So in this case, but this is only for 1D problems and not more. But more generally, time is not observable. This is a parameter. But what is a parameter? Very interesting question. Would be really interesting to discuss it.
Okay, thank you.
Yeah. But this is because this is parameter when technically this is parameter when you decide to measure this state. So this is not characteristic of the system itself. This is a parameter of your decision. But you can, for example, do your measurement device, the whole apparatus, Here is source, for example, photons or electrons or whatever, Here is your device. More or less, you understand when it happens, T, So in this case, this parameter can also be estimated. But the question is very interesting.
Thank you.
Can I also ask about this? So we have like maybe this stupid question, but like we have a
we have no stupid questions.
We have a translation symmetry which leads to the momentum conservation, and then we have a time translation symmetry which leads to the energy conservation. So my question is like, how can be one thing be observable, another thing be a parameter in this sense? Like I don't,
Anton, I should say that I'm interested in this question since my even not PhD study, but since my maybe master study when I was student. Can only tell you that I cannot answer your question now unique. I don't know. Sorry. in this case, because it seems to me that sometimes I have answer to this question. I read a lot of papers about this, but after that I simply find another points of view, and they also looks to me very, very correct. So, but question is incredibly interesting. Yeah, very fundamental. Yeah, and not stupid. Stupid is my answer in this case. Yeah, your question. Yeah.
So we have also questions from chat. Is it possible that probability distribution of quantum state with reference to some observable, say energy, has no density, like counter function which has zero density almost everywhere in Lebesgue measure?
Just a moment, I didn't get the total question. So
okay, so again, is it possible that probability distribution of quantum state with reference to some observable, say energy, has no density, like counter function which has zero density almost everywhere in Lebesgue measure?
Okay. This is not density. This, for example, when this is, if I understood your question correctly, for example, if you have a discrete observable, this is not the density probability already. We describe it as a probability distribution, but this will be probabilities. Yeah. Is it? Do I understand correctly this?
I'm not sure. Please specify your question.
Yeah, you can specify your question. You can also use for such question. For example, we have WhatsApp chat. You can write here, and maybe today evening I will try to read it. Yeah, when I didn't answer something.
Okay. Other questions?
Yeah. Another, so this one which we skipped concerning the response function.
Let's return back to this question later. We have a question related to this part in our room.
Okay. Sorry, I just can't see the room. So yeah.
I'm just not sure that related to that part. I want to ask some question when we talk about time. Is it any principal difference between time and time intervals? In that case, can we say that we can measure time intervals in quantum physics, or it also estimation?
Yeah, you see, I in principle do not want to use the word measure when you say about time. You see? Yeah, this is not measure. Maybe this is in this context, of course, yeah? Of course, nobody, this like with temperature, nobody said we will estimate temperature, yeah? So everybody say measure temperature, yeah? But in this context, in this sense, this looks like a jargon, yeah? Again, with time, story is really interesting. There is even now direction of this relativistic quantum information where people try to combine relativistic things, special relativity, with all we know from the quantum information. Yeah, and one of the questions here is exactly about time. I do not give at the moment to you some questions that will be that I will be sure in this answer. I cannot do it, unfortunately. I would be happy to do it, but maybe I do not know something. Okay. But in my understanding, there are a lot of here uncertainties, yeah, in this, in deeper understanding, what is it?
Okay. So we can return back to the questions that was earlier, but related to the previous part.
Yeah.
Please, Anton.
Yes. So we have also a new question which is related to the current. Is the characteristic time of change of some observable is observable itself?
No, not. This is, I understand, this is you mean characteristic phi time of measure of changing some observable in the in the context of time energy uncertainty relations, if I understand correctly this question. In this case, not. This is not an observable, this characteristic time, because you cannot get the value of this quantity from a single measurement.
Okay, other questions?
Yes. So, please, I'm a little confused as a delta function is an input that produces an output, especially in linear time variant system, mechanical oscillators, and so on. So the delta function will be an impulse, not a response function, right?
To be honest, I didn't get the total question.
When you describe
when you describe, you mean
classical oscillator?
When you describe classical oscillator,
Yes,
you mean
somewhere.
When you describe pure state of classical oscillator, for example, you can also consider rho from QP. So this case as this function as a delta function. In this case, in this concept of rho from QP, your classical states, your pure classical states, will be described by delta function.
Yes.
Yeah.
Okay, the next question.
When this is, I correctly understood question. Maybe this is about a response function. I don't know, but maybe this is about this one.
Let's move further.
Yeah, but you can always use WhatsApp chats for our school. Yeah. And maybe later I will try to check it.
Anton has questions?
No, that's it.
That's it. Okay, dear colleagues, I think we should have a break right now.
10 minutes.
10 minutes, and after that, you can continue.
Thank you very much. So let's go. Main very short thing that I should only mention to you about time evolution, because I tell you, when we build our theory, we should have what? We should define what is state, what is observable, what is measurement rule, and last but not least, Schrödinger equation. Oh?
Everything fine?
It's okay? No.
Some checking problem.
Yeah, sorry, we have, yeah. Okay, and quantum state is also evolving in time. And you know that how it evolves, I believe many students understand it, that this is according to Schrödinger equation. We have such an equation, differential equation, to be honest, that here is derivative on time from the state is equal Hamiltonian on the state itself. We can solve this equation, at least formally, even very easy when Hamiltonian does not depend on time. Let's consider it does not depend on time. In this case, you can, many of you have been studied maybe this theory of partial differential equations. So the solution can be written like this, at least formal solution. You see that in this case, you have to know eigenstates of energy, and so you should solve time-independent Schrödinger equation, and this is time-dependent Schrödinger equation. And eigenstates, eigenvalues of energy. And this amplitude depends on the initial state. When your initial state is, so this is simply like this, but scalar product with initial state. Okay, this is not I want to show you many times, to show you exactly how this works, because time evolution for our things will be important sometimes, but you simply should know how this works. Okay, let's now make a checking list for pure quantum states and projective measurements. What I told you so far is called projective measurements, because this is described by such things you will see a little bit later, which calls projectors. So these elementary measurements, these ideal measurements are called projective. In this case, pure quantum state is a vector, is a very strange vector in a very strange space, okay? Quantum observables, operators or matrices, all this is related to real physical worlds in terms of Born's rule, which is written like this, and we have time evolution as Schrödinger equation. Okay, and now what we want to do. I will not stop because I already answered a lot of questions before, yeah, because when I will answer another question related to this after that. I believe here we have checking list. It's clear to you. Okay? Yeah. And now let's go to realistic world, because not in the world everything work like this, with ideal pure quantum states, with ideal measurements and so on. So we should now broken everything to be more close to experiment. Okay, let's start with new concept. It was just before coffee break, very nice question about, I don't know, maybe I do not understand it correctly, maybe it was related to another story, but how to write pure quantums, pure classical states in terms of probability distribution. So pure classical state, this is not only QEP, but rho from QEP, this is delta function. Okay, also. Very similar concept, like a probability distribution, exists, this function, Liouville function, exists in quantum mechanics. And now let's, in order to show you this, I will start with another alternative description of quantum states. Now I will say about very important things, try to understand it. Instead of vector psi, cat vector psi, I can now describe my quantum state by such an operator rho, which is called density operator. In some older literature, it calls density matrix also. For pure state, and this is like this. You see that this is matrix, I told you before, yeah, the adic product. Psi times C. You can see that mathematically, this is the same, because each vector, to each vector, I can map on one operator and in inverse direction, yeah? For each such operator, I can map such vector. Here, there exist some very important things. First, how looks some properties? I should rewrite now a lot of things in this new formalism, not with psi, but with rho. This is simply another language, okay? Now this is almost the same. So you will understand a little bit later why I need it. Normalization, psi is like trace, rho is 1. What is trace? Everybody remember? Sum of diagonal elements in any basis. Born's rule, which were looking like this, now is rewritten in such a form. Look here. PAN is trace rho, and here we have again projector, but on eigenstates. Okay, I can write that this will be AN rho AN. This will also be true. But for some reasons, I need such a notion. Because this is a school, I can give you some exercises and you can try to solve them, okay? This exercise, I already asked you questions, some, and here will be some exercises that you can try to prove that this and this is the same, and this is the same. How to do it? I have some related math. So this is a little bit tricky mathematical question, not really, but tricky. So first of all, we should understand that eigenstates and eigenvalues of Hermitian operator can be expanded in series like this. Look here, I already put Pn, these coefficients here in explicit form. You see? I have put it here. And look here what happens. I have this vector psi, and here psi. But this is some operator, sum with n, an, and n. It acts on psi, and you have again psi. What is this operator? Unity operator. Completeness relation or resolution of unity is called. So you should use this fact. And of course, you should use definition of trace. So using this math, try to prove this corresponds. So the second, this column from the first column with such a definition. Okay? So, once again, very important. I now presented no new physics. I simply have presented new language for description quantum system. This is the same as I have described, for example, pure quantum states with Q and P, and after that I described pure quantum states with delta functions. Yeah, we draw from Q and P, which are delta functions. This is full analogy of these delta functions. I will need this density operator more. Okay, and now what I would like to say that what you should study from this, that because you have this trace, you should understand one physics, or believe me, yeah, because this is quantum mechanics, that this trace, the tracing here in quantum world with such operator, this is like averaging. When I should average something in classical world, I should take integral. I should take integration, okay? When I should average something in quantum world, I should take trace. Trace in quantum world is the same as integral in classical. I understand this is hard to believe, but please accept it. Okay? Trace is averaging. And another story that I would like to introduce you now is really strange things, is really paradox. How in quantum physics appears mixed state. First of all, let's consider how it appears in classical states. It's simply lack of my knowledge, yeah? For example, I have this pointer, I can keep it there or keep it here, after that forget, and I will have probability distribution where it has. It exists somewhere, yeah? It's simply my lack knowledge of where is it, yeah? In quantum physics, mixed states appears totally different. No, they also can appear in such a way, but they appear totally different. In order to understand it, let us consider that our system A interacts with such an environment B. There is interaction between system and environment, A and B. A can be system, B can be environment. Also, it is true when you consider that A is a system, but B is a measurement device. But in this case, after my all consideration, we will have to do one step more, one very strange step more. But I will not even discuss it with you, but maybe at the break we can discuss these strange things. Quantum state reduction, it calls, yeah? Okay. Now, our Hilbert space is really strange. After this interaction, I can write vector psi as such an expansion. Look here, AN is some basis for the system A, orthogonal basis. BN is some basis for the system B. This is also orthogonal basis. There is well-known mathematical theorem. Any quantum states for this two-component system, I can always write in such a form. You can tell me what is surprising here. You can always expand in series some quantum state. But this is not simple expanding in series. Because here, you see, do you understand what means this circle, this cross? Yeah, tensor product. Yeah, exactly. This is standard product. Yeah, this means. And this simply when you have different degrees of freedom. So you have, for example, this is for system A, and this is for system B. Yeah, A for system A and B for system B. And when you try to expand, you simply need sum over two indices, N and M. Nevertheless, there exists theorem, very nice theorem, very deep theorem in linear algebra, that you can always find such basis that you will expand it only with one index. This is called Schmidt decomposition. Okay? Now, what I want to consider, I want to write density operator for this conglomerate, system plus environment. Very easy to do. Just transpose it and multiply. Rho is psi, sum nm, cn, cm conjugated, of course, and simply write these two projectors, an, am, multiplied with bn, bm. Actually, it's everything very easy, yeah? So far, nothing new. I simply rewrite this in new language. Where appears new things? New things appears when I'm trying to ask myself, what is the system, what is the state of a system A only? How to do it? How do you think? I'm not interested in, so A is my, I don't know, electron, B is all molecules in this room. I don't interested what is these molecules. I'm interested only in I'm interested only in state of my electron. What should I do? Yeah. Exactly, trace. Partial trace it calls. Average only with environment, only with system. I should average it only with system B. Or this means tracing with system B. This calls not trace, this calls partial trace. Okay? Okay, and it we can write it like this. Rho A is trace B rho. This is something like this. And definition is very easy. Sum over some index k with these basis vectors bk, rho, bk. Not difficult. Sounds easy, yeah? Let's do it. Let's substitute this rho into this equation and see what happens. Okay, I have substituted it. Look here. You can simply rewrite for you, yeah? You see, this is now sum over k and m. Two coefficients, cn, cm is 0, still exist. An, mm, projector, nothing happened with this. But with bn and bm, we have from 2 times these brackets. But you know that this components, the scalar products, this is from 0 orthogonal, yeah? 0 orthogonal. And this means that this is Kronecker symbols. So now I believe people study mathematics very well. They know what happens if in sum we have Kronecker symbols. Do you understand what happens? Indices simply kills, yeah? We kill two indices, n and m. As a result, we have such a very easy relation. You see? Sum over k, ck, modulo square, ak. What is very interesting to, okay, I should wait a little bit, but I will show this. So, okay, write it. I will wait a bit. This coefficient ck here have very interesting property because actually this is expansion coefficient, yeah? This means that sum over modulo square of these coefficients will be 1. And because this is modulo square, they are positive definite, yeah? So, for these coefficients, we have something like this, and we can interpret these coefficients like probability to find the system in the pure state AK. Okay? And because density operator now can be written like this, look here, density operator of subsystem rho A. This is sum over k, pk, ak, ak. This is already mixed state. This calls mixed state. Before I go further with mathematics, let's think what we get. We get really strange things. This is already a quantum paradox. This is very important things. This is called in the literature entropy of entanglement. Okay? And because this state when was between system and environment was entangled. Yeah. You see what we have. We have two systems. Okay, I will take this one and this. Can I use it? We have all this system. This is system A, this is system B. I am totally classical person. I have total information about states of this system. I know position and velocity and momentum of this, and I know position of momentum of this. It's a really strange question in this case, in classical world, to ask that if I know, if I have information about states of this stuff, of this pointer. Okay? But in quantum world, this is not strange question. In quantum world, if I have complete information about the whole system, I know exactly its states because it's pure state. I know everything what I can in principle know about this system. It doesn't mean that I have information, exact information about this subsystem. You understand it? It's really strange. Of course not. I also. Once more again, in classical physics, the question itself looks even strange. I know exactly, I have 4 numbers for these things, okay? Of course, this means that I know these 4 numbers. In quantum physics, if I have exact information about the whole system, system plus environment, or this is 2 systems, for example, some systems which are entangled, the states, or it should be entangled. It doesn't mean that I have exact information about its part. This is how mixed states appears in quantum world. Of course, they can appear also as a lack of our knowledge. It's also a possible mechanism. But this is a very specific mechanism which exists only in quantum world, in this strange wired quantum world. It's really wired. You see? This is really, I know where is this table and this table. But when you ask me what is position of this table and for you is an irrelevant position of this table, so I will not know this. In classical world, it's stupid. It's a strange question. In quantum physics, this looks like this. Okay, this is mechanism how appears mixed states in quantum world. Let's do a little bit more formal things. Let's define now what is in principle quantum mixed quantum states. This is density operator. We should write it like this. Cn is not necessary, should be orthogonal, should be orthogonal basis. It's not necessary. Nevertheless, when this is orthogonal number basis, you can say something about Pn and Pn. How do you think? What is it? When this is orthogonal basis?
Probabilities.
No, mathematically. Yeah, but what is mathematically? What is the object of Pn? What is Pn and what is Cn for operator rho? When this basis is orthogonal, eigenvalues and eigenstates. Yeah, eigenvalues and eigenstates. In all cases, they should be positive. Some should be 1, and the state is called mixed if does not exist such vector psi that rho cannot be presented like this. If you cannot present it rho like this, like pure states, okay, this is mixed state. And this is why we need this strange density operator. Because you see, it turns out that not all quantum states can be described in terms of psi vectors. There are a lot of vectors, quantum states, which cannot be described like this. Okay, there is more formal conditions for these properties, because when you, for example, theoretician, and you get some operator rho, you should be sure that this can exist somewhere in the world. Yeah. For example, you need such states which is described by such density operator. In this case, two very easy properties. Very strange relation, rho is more or equal 0. How do you think, what does it mean? Operator is more. Strange notion, yeah? It simply means that eigenvalues should be non-negative. Yeah, okay? It's a very short distinction. And trace rho should be equal to 1. So when you have such operator, this means that we can build related quantum state. One more gain. Our example with temperature, but already in quantum world, yeah? Thermal state, which is written like this. Now this operator 1 over z, simply some normalization coefficient. It doesn't mean how people in statistical physics, call it, yeah? Yeah, and here, in minus h in k Boltzmann t divided. So this means that you can easily see that you can write it like such a sum. Sum over n, you can simply do very easy exercise and to understand. 1 over z, in minus n k Boltzmann t, n. n is eigenstates of the Hamiltonian. Pn, your coefficients which are here they are. Once more again, temperature T here. This is just an example, believe me. Temperature is only an example. It's not an observable, but a state parameter, and it is not measured, but rather estimated, okay? Temperature. When you have, for example, in quantum optics, I told you that quantum optics, one more in quantum optics, it's also an oscillator, yeah? Harmonic oscillator. Not mechanical, because this is field quadratures, but harmonic oscillator. And in this case, temperature may also exist. And you may estimate that temperature appears to be really related to field intensity, or this is some parameter which we should estimate. This will be estimation like intensity, really, what you tell before, what Professor Kurduk told before us. So this really estimation, and I believe on Friday you will hear about how to do it. All your questions, I believe, in the lecture by Giacomo Sarelli. Maybe he will speak about it a bit when he go beyond, or in the lecture of Professor Lvovsky. I don't know, but somewhere you can listen even about experimentally how this looks. But this is estimated. Okay. I have broken quantum state. Yeah. It's already broken, totally. Shall we do some pause? I have.
I think we can continue.
We can continue, yeah? Okay, let's continue, yes, and after that we can do, yeah.
Yes.
Okay, because we will have more time for questions, maybe. Yes. Yeah. Now, what should I do? I'm going to another concept, important concept to you. I'm going to another concept about more general measurements. Now I should broken measurement device. So, experimental people should not afraid. I'm not going to the lab to broken it physically. I simply want to describe it theoretically, okay? And let us consider an example. Let us consider an example how to do it. We consider now more general measurement which exists. Let us now consider that we have measurement noise. You have very strange measurement device. It, in principle, wants to measure some observable or some value an, and it has an an. For example, an can be, in order to be more close to reality, it can be the number of photons. So this is simply number 0, 1, 2, 3, 4, 5. But something happens in this device. Some photons accidentally can scatter, and you have not registered them. Or some internal sources, for example, there is some glass from quartz, and there are some radioactive element, yeah, and it radiates gamma quants, and it also gives you some pulses on this device, on your photo counter. You have some additional pulses, for example. So this means that you will have randomly some additional noise. Instead of AN, you will see some BM. So instead of 2 photons, you will see 3 clicks on your photo counter, okay? But with probability, conditional probability, P, probability to get BM, given the real number AN. So this means that I have already 2 photons, but with probability like this, I will get 2 photons, or 3 photons, or 1 photons. Okay? Are you familiar what this means, yeah?
So this is our assumption.
Yeah, this is our assumption, but actually this is what we usually know about measurement device. Yeah, okay, now this is or from some theory or from some experiment or I don't know, some vendor gives us such characteristics. So this can be, some information can be extracted. So this is our task to get this information. What we can do? We can now do the following. We can use now the law of total probability. Okay, yeah. Microphone, just wait, please.
So our goal was, when we constructed this device, for example, was to measure the probability AN. But Mario says what this device does, it measures the probability that we'll get some other results which are BM, given that we have AN. But how does it help us measure AN? And is this like totally different device?
Thank you. It does not help us in reality. Yeah, it doesn't help us at all. Because if you have this device, you have only access to BM. You see? Once more again, just consider photo counter. Yeah? Photo counter is some device which, so you have, for example, some detector, you have some radiation field, and it counts you 1 photon, 2 photons, pulses simply, yeah? It can be that some extra photons come, it calls that counts. You cannot distinguish between this and this. You don't know what is true photons, what is photons that comes from environment, yeah? You simply don't know what is it. You simply should count it. And unfortunately, this is what you have. You should consider this noise. You have noisy device. What we want to describe, but this device will include information about your true signal. Your task is to understand how to use this information with the largest capacity. Yeah? So you should understand how to use it and how to make it useful for you, because it still exists some information, but this information, yeah, it's noisy. Because device is now imperfect. Sorry, but this is the word. It's how it works in the real world. We, in principle, word is imperfect, and yeah, perfect devices does not exist. Instead of what's example, but experimental people didn't convince me so far. Okay, haven't convinced me. Yeah, okay. What we can use here? We can use the law of total probability. I believe everybody knows this famous equation, yeah? When you have true probability distribution, P from AN, or you suppose, you can write such an equation, because this is the law of total probability. About Bayes theorem, everybody listen of you, I believe, and you're okay with this equation, yeah? What I now want to do, I now want to substitute here Born rule in this PAN. Here I can use Born's rule because this is true probability distribution. Okay, let's do it. Let's substitute here in this equation simply this Born's rule. I have substituted it here now. Sum PBM given AN, trace rho AN. This is Born's rule. Have you recognized it? Born's rule written in terms of density operator and trace. Yeah, recognize. What I can do now, I can change trace and sum. Okay? By places. I will get such a relation. Trace, rho, and here is sum over n, P, BM, AN, AN, AN. And look what I have. Actually, I have what I need. I have a relation which is very close to classical word. Now, this is some operator over this sum. This is some operator, and this operator I can use symbol P, Greek P, hat from BM. It really depends now only from BM. And this is actually what we call positive operator valued measure, POVM. Related measurements are called POVM measurements. And don't forget, this is just an example. This is just an example. There is more general type of measurements. We will talk about it. I will talk about it. Now, I can write Born's rule in the most general form. Look here. Probability to get value BM, I still use here BM. After that, I will use A, okay? But now, because B, this is something broken observable, yeah? I use this one. This is trace rho with P, B, M. And you see now, very good analogy with the classical word, maybe. Just write this equation, and after that, I will return to the first part of my lecture. This is actually, this equation is the purpose of my lectures. You should, in order to you understand tomorrow lecture from Gerardo Odessa, from Professor Odessa, you should clearly understand this equation, this generalized form of Born rule. Do you see analogy with classical? We had there not trace, but integral, yeah? We had here rho as a probability distribution function, Liouville function, phase space probability distribution, yeah? And P was device response function. But this is how things are working in quantum domain. This was just an example of more general POVM measurements. In general, more generally, I should tell you that what we have, that the POVM, so there is, in principle, you can construct a lot of different measurements, a lot of different operators. So POVM, what is POVM? POVM is a set of operators, mathematically. And this set of operators should satisfy two conditions. First of all, they should be non-negative, positive semi-definiteness. Their eigenvalues should not be negative. The second condition, completeness. Yeah? Because it should be normalized. Sum over all BM should be 1. This example that I have shown to you is only an example. This is only an example. This is nothing more. This is only an example. There is more general kind of measurements. And when you, as a theoretician, have shown such a family of operators which satisfy these two conditions, you can say that in principle there exists, at least theoretically exists, the corresponding measurement device. If you an experimentalist and you tell me that your measurement device is working something like this, I can always find, or I can try to find, because this is very difficult theoretical question to describe this device. I can try to find this family of operators which calls as positive operator value measure. So our task of theoreticians is not only to solve Schrödinger equation, is not only to find density operator quantum states, but also look at the measurement device and to find this P of n in order to see what experimentalists see in the real world. Okay, it looks like I'm going to the end of my lecture. So a little bit earlier, but lunch is not ready, but okay. I summarize and after that we will have questions.
Yes,
comments.
yes, I suppose we will have questions.
Yeah, we will have a lot of questions. I suppose we will have a number of questions. Now I will have a lot of time to answer them. That's very good. Let's make some summary. What we have studied. Pure quantum state. We understand that this is a vector in the Hilbert space of states. This is my checkpoint from the first year, was like this. Mixed quantum state. Density operator, I hope you understood what is it. Okay? Quantum observables. Ideal quantum observables, yeah? This is operators, they can be measured, they can be maybe measured, so this is Hermitian operators. Bond's rule, the most general things, and this equation that I ask you to, all of you to understand, because lectures and other lectures will be based on these equations. What we use in quantum metrology, this will be used on these equations. And time evolution is given by Schrödinger equation or its generalization for density operator. Just look at the one. When your density operator, so what will be next? Just a little bit announce what will be next in the school. Imagine that your density operator, your prepared state, is dependent on some parameter. Usually we say not t, but Greek letter theta we use. In this case, this probability distribution also will depend on this parameter. Yeah? And the task of quantum metrology will be, this is for parameter estimation, better to say the task. We made a lot of experiments, have some statistics. Okay? Having these statistics, we have a hypothesis that this is our probability distribution. And from these two facts, we want to evaluate this parameter. This is next question after lunch. We'll, in classical case, only for this, for PA, we'll tell you about, this will be a lecture by Professor Pilipenko. And after that, we can be interested in question, but what is the best accuracy we can get when we use all possible measurements? And this is the subject of quantum metrology. It turns out that there is some quantum limit for such estimation. So quantum metrology, it's about estimation of parameters. I really hope you understand the difference between measurements and estimation now. Okay? So this So it's unexpected to me because I thought I will talk more, but okay, sitting on front, we can use some time.
We have some time for questions, please.
We have a lot of time for questions because lunch will be only at 2 o'clock.
Yeah,
I believe. Yeah.
I hope so. So please.
If we have a lot of time, maybe you could give an example. For example,
Just a moment, a bit louder.
if we have lots of time, maybe we can give an example for Bourne's rule. For example, a simple spin system or for oscillator, and just write it.
Yeah. I can do, but this will be for people familiar with more or less quantum mechanics. Okay.
Yes.
Okay. So which that one? This one? This will be seen in this. Can you just just a moment? I will take something to write. In quantum optics, you have, for example, very basic measurement device which holds for the counter. For the counter may count you the number of photons. 1, 2, 3, 4, 5. Okay, and even more. This means that there is an observable which we can measure. This observable is photon number operator. Okay? This is like if you familiar with quantum mechanics, this is like in harmonic oscillator. So number of excitation in harmonic oscillator. And eigenstates and eigenvalues are very similar in this case. Those are simply numbers. Numbers of photon, ideal photodetector. 1, 2, 3, 4, 5. If I want to measure the number of photons, my POM will be, or it's even not POM, this calls projective operator value measure. Why? Because in this case, this will be N. Okay? So this I would say that this is my PM. Is this like this? And I can use it in Born rule. Yeah? But this is very, very ideal situation. What can happen? Can happen that you may have, for example, some extra photons. They can come. Okay? You may have, for example, this some. So, for example, you always have some additional source of photons. Instead of number n, you have another number m, which is n plus k. Okay? This is, we can consider as independent Poissonian source. This is actually what we have, for example, from this law. If you put now for the counter, yeah, and no other sources, this is not interfere with your source, you will have simply Poissonian nodes. This means that we have probability distribution. I will write it from K. This is nu K over K factorial. And here is Y minus nu. So this is simply your photo counter will have such a noise. Yeah. Now, what you get, you will not measure n, you will measure, I'm sorry, this m. Okay? Yeah, and this is what you should understand from this m. Yeah? So you should now, let's think how to do it. You should now write that your P, okay, I will write here like in this, in my lectures it was in brackets, but I believe you understand, yeah? Yeah, PM, but this is another PM, that will be with tilt PM, noisy PM, okay? Sum over some number n, say, here will be P n Oh, let me think about this. Sum over P. Okay, this will be N maybe. P M conditioned with N, if I write it correctly. Okay? So there is such, so this is a probability to get M clicks under conditions that I have N photons. You see? Now I should write this probability distribution in a little bit more correct form. Okay? So let's think how to do it. So that's just, I didn't prepare for this, but...
So PMN, this is your portfolio liquidity.
Exactly, this is this one. This is this one, yeah? And here, what we have, we can write this because you see from here, you can see that K is M minus N. Yeah? What we have here, now we should put it here. Let me simply to do like this. So this will be new M minus N, M minus N factorial, yeah, minus nu. The only question is possible values for N. When you have M clicks here, your N cannot be any number because this cannot be negative, yeah? Here. You cannot have negative number of real photons, yeah? So this means that this is N from 0 to M. Okay? But this is not all. This is very nice equation, yeah? But this is not all equation, so this is already P of M, this example of P of M. What you have, when you have that counts, yeah? But we can write it even more nice form. Because what I can use, I will write you now equation, which maybe not everybody understands in this audience, but I believe that some students try to understand. There is very basic equation that this projector N can be written in the form. Are you familiar with the concept of normal order? Yeah. Some students yes, some students no. Yeah.
Maybe the right.
Look here. The point is that this operator N is written like A deca A. What is A? It's do you have okay. Very easy to show you. Let me just go at the first slide of my lecture. In this case, I can explain you. Just a moment, just a moment, just a moment. Okay. You see here alpha, complex amplitude of the harmonic oscillator. When I quantize electromagnetic field, instead of alpha, I have A. Instead of alpha conjugated, I have a delta. Okay? Intensity, in my case, this is simply module alpha square, but the number of photons I deca R. What is normal ordering? Normal ordering, this is when you have, for example, A deca, A deca, A deca. Let's see. And after that, I'm using such 2 points. This is simply, I should put here all this operator A deca, they called creation operators. A called annihilation operator. This will be A deca square, A square. Okay? Why do I need it? Because in terms of normal ordering, this is very easy to write. there is exceptional equation. This is, look here, null bar ordering from n in n factorial minus n operator. I will not tell you how to prove this relation. This is any textbooks on quantum optics, practically any. And look what happens. Let us consider, first let us consider how this works. For example, if I have single photon source, for example, single photon source, yeah? So my state rho is 1, 1, okay? I'm doing tracing this with this. So I'm interested. P, N, N is okay. This will be trace N. N, I will use this representation now, okay? But here will be also multiplied with 1, 1. You can easily prove that this will be N 1 module square. And this is delta 0, 1. Delta N1, sorry. So, okay, single photon source, you have a probability to measure only one photons to see in ideal detector, yeah? Okay, but let's see what happens next. There is another story.
It's the probability to measure n if we have one photon.
Yeah, if you have one photon at input. There is more interesting sources. Are you familiar with laser? There is such a device. It radiates very interesting ideal laser. Radiates very interesting radiation field. It's called coherent state. Coherent state is an eigenstate of operator R, which is not Hermitian operator even. R alpha is this number alpha. So when you have laser, your laser is always radiates something like this. Okay? And this is very interesting to see when we consider here rho is alpha, alpha. And you now substitute this here. Okay? So this will be P and trace alpha, alpha. And now I use simply this equation. N factorial minus n. You can write that this will be again alpha with this operator n over n factorial minus n, normally ordered. But because of this definition, so here, all, so when you expand it, it's series, all annihilation operator R will be right hand and all creation operator left hand. Because of this, this will be simply alpha to n over n factorial minus alpha Poissonian distribution. Okay? But this is ideal detection. Let's see what happens if I use this equation with dark colors. Okay? It's also a very nice equation because in this case, I have to substitute this one here. Okay? I simply write like this. Okay, let's do it. N from 0 to m, nu m minus n, m minus n factorial, minus nu. And now I'm substituting this one. N over n factorial, minus n. So what I can do, first I can write like this, normal ordering, okay? And I can put it over the sum. Minus n minus nu, okay? After that, I have here n from 0 to m, nu n minus n, here n, n, and here n minus n, factorial, and factorial. I believe you already understand what is it. No? I can multiply it and divide over n. Look here, can write m factorial, and here m factorial. Binomial formula. Yeah? So, and here normal ordering, of course. So you have, for example, 1 over m factorial. So what we have from here we have simply n plus nu in m. Oh, of course, I should put here normal ordering, yeah? And yeah, in minus n minus nu. Voila. We have P of m with that counts. Yeah. When you use now this, for example, you can simply do easy exercise. You can try to understand what happens with single photon state and with coherent state. With coherent state, this will be still Poissonian distribution, but with another mean value. This will be modulo alpha square plus nu. Yeah. For the single photon, this will be a little bit modified Poissonian distribution. This is not all. Answering your question, because I now show you, because maybe really good question, because maybe some lecturers will use it. And this is quantum optics. But they will explain you also these things. This is not only the point when we have not only this problem with photon detection. Because with photon detection, we can also lose photons. You see? So it may happen. And when losing photons in photon detection, there exists such a quantity which calls detection efficiency. Detection efficiency, eta. This is some quantity, parameter, by the way, but not state parameter, device parameter. Yeah. So you can discuss more with Mikhail about it, by the way, what this means. Yeah. From 0 to 1. When this is 0, this is perfect detection. When this is 1, this is perfect ideal detection. When this is 0, this is nothing. This is simply you don't have detector. Yeah. Or you put some, I don't know, how to destroy detector, Alexander? So we simply totally destroy it. Yeah.
Well, it means that it doesn't detect.
Yeah, it means that it cannot be detected, simply darkening. Yeah. What do we have in this case? In this case, I can write my view.
I just want to specify. This is it means that we do not obtain photons.
Yeah.
But photons that we want to obtain, but we can obtain photons from other sources. I mean, we count n photons that we want to count.
Yeah.
But also we don't want to count photons n.
Yeah. It's also possible. It's possible. No, it's possible two scenarios. For example, you have detector without. Let's imagine a detector, such an idealistic detectors without dark counts at all. Yeah. How this equation will be rewritten? In this case, Pn, if n, but here I should simply multiply for the number with n. And this is actually all. But when you have this loss of photons and plus that counts, okay, so this will be even more. In this case, my P of m will be For example, something like this. Eta n plus nu n divided by n factorial eta minus eta n minus nu.
So, and in this case, if eta is 0, it doesn't mean 0.
It means that you count only the counts.
Yeah. You don't know. It's just that counts or
not. When you know that your eta is 0, then you know this exactly, unfortunately.
Yes, you know exactly. But in this case, you can estimate the number of duck counts.
Yes. In this case, in this case, exactly. Exactly in this case, you can estimate the number of the counts, and very easy estimate because this will be simply a mean number of these counts. So you can, exactly. This is parameter estimation problem, but not state estimation, but for the parameter of detector estimation. But also, it works like this. This is just examples. Another example of POVM in quantum optics. Maybe some lectures will be on Friday told about it. Field quadrature, Q. There is a procedure, I will not tell how it looks like, but it calls balanced homogeneous detection. And with this procedure, you can measure something like this. This is like position measurement, but only for electromagnetic field. It never works like this. It should also be integrated. Here you will have some function Q prime, maybe here Q prime, D Q prime. And this will be some P from Q POM. Another lectures will use for you, I believe this will be so like this, not Q like this, but like position of photons. This is when you consider imaging problem. Okay. And in imaging problem, your POVM indirect imaging, because you will also consider indirect imaging. In this case, your POVM, this is position operator. I'm writing not Q, but X. Your POVM is something like this. This is simply how it works. This is CCD matrix in your camera, okay? So this is this device. When you put here single photon, only single photon, and you're sure that your photon is single, this device will be described with this. Of course, also because pixel is finite size, so it should be cross-grained and so on and so on. So the word is not perfect. But I believe I answered your question.
Okay, thank you very much. Probably we have some questions, maybe not so extended, but short questions related to the last part of lecture. So please think. Yes, Alexander.
Could you go back to the slides about the quantum mixed states?
Yes. Maybe we should switch off the light. Where is it? Okay, thank you very much. Thank you, Sergey. So, the definition of mixed state, yes?
Yes. Here, this one.
No definition, but...
let it be this one, it's okay.
Yeah.
So, we use the Schmidt decomposition and this relation between system A and system B to define quantum mixed state, right? But
not to define quantum mixed state, but entangled state between these two systems. Initially, it was not entangled. After that, they interact. And as a process of interaction, Schrödinger evolution appears such a state.
But I'm curious, does it mean that every time that we talk about a quantum mixed state, even if you don't say it explicitly, we mean that there is some environment, system B, relative to which this is the representation of this state, yes?
Yeah, and this is the problem of decoherence, actually. A very serious problem when you consider why quantum computers don't. Yeah, it will work maybe. No, they don't work like we want. Yeah, Because of this problem, because there is interaction with environment, and instead of pure state, we have mixed state. Yeah, this is called decoherence. Yeah, this is huge problem for quantum computers. So physicists and the whole world around, experimentalists, engineers, do all possible in order to isolate quantum system from environment. It's relatively easy. Okay, for me as a theoretician, it's easy to say. Yeah, relatively easy to more or less isolate single qubit. Yeah, single small. But when you have a large qubit system with thousands of qubits, or what they need, millions of qubits, when you need to isolate it and when you need to control it, moreover, it's really a difficult problem. And this is unfortunately how it works. Yeah.
Okay.
So yeah. In realistic worlds, states usually are mixed. What we consider as theoreticians as pure states, coherent states, laser, they're also not pure. It's also not like this. But with very, very good accuracy, very good laser can radiate something that we can describe as a coherent state.
Okay, thank you.
I have a related question from the audience, very related.
Yeah, Anton, yeah.
So Roberto asks, doesn't the mixedness of raw come, at least in part, from the measurement noise? Wouldn't raw itself depend on PBM?
Wouldn't raw itself depend on
P on the probability when you're talking about the POVM operator?
Can you write question from the beginning, Anton?
So doesn't the mixedness of raw come, at least in part, from the measurement noise? Wouldn't raw? Can you switch to the slide with the POVM definition?
With POVM this definition? Okay, this one?
No, next.
Next one with the POVM definition.
Yeah. Here.
Yeah, okay.
So wouldn't raw itself depend on PBM, and doesn't the mixedness of raw come, at least in part, from the measurement noise?
In this case, not. In this case, not, because so you can, in principle, consider more complicated story, but the problem is that with raw we can consider now separately stories that something wrong may happen with raw, and something raw may happen with your measurement device. But this is a very philosophical question: what is your measurement device? Yeah, because what you may have. If you, for example, have detection losses in some fiber, yeah, so you have fiber, it lost some photons, and after that you have a detector, yeah. So detector is described with something, some POVM, but you can also consider detector as a fiber plus detector, and in this case you simply transfer this noise of fiber from your quantum states to the detector, yeah? But you should also, in this picture, you should also consider when you have a system and detector, you should always clearly say, at least for yourself, what is your system and what is your measurement device. Sometimes it is not clear, yeah, because like in this example with source of light, fiber, and detector. So detector, this is only detector, or detector, this is fiber plus detector. Depending on this will be, you will put this noise or in raw or in detector. I believe this is what was the question. But when this device, in raw, there exists no dependence on BM in this case, because device is something independent.
So yeah, if I understood correctly, it means that like density, like the coherence of the density matrix may be caused by the environment, but when we're talking about the measurement or PV, it will have the probability distribution, which is related purely to measurement device, right?
Yeah. Because you see, measurement device, this is simply another environment. Okay. With measurement device, what I should mention what I didn't say, maybe it would be nice to say for all of you. When I have, for example, just mentioned that this is measurement device, okay? That system B here is measurement device. And you have this mixed state. Have you ever seen in measurement device that this is mixture of 1 photons and 10 photons? You haven't seen it. You see only or 1 photons or 2 photons and 10 photons. What does it mean? This means that at this time happens quantum state reduction. From these possibilities, only one single possibility is realized with this probability. So not only measurement device, this means that its states are macroscopically distinguishable. So because when you your detector absorbs 1 or 2 photons, in theory, I can see it that this absorbed 1 or 2 photons. Microscopically, I can see it. You do not see superposition of 1 and 2, or some mixture of 1 or 2 photons. You see that something happens. This means that at this moment happens something that is not described by Schrödinger equation. Yeah, this is what people say quantum state reduction. I didn't want to tell you about it because this is really a philosophical question, but this is a realistic situation.
Okay, another question, please.
Yes, so maybe to clarify the whole thing, would you mind saying us a few words about the difference between the probability distribution that is associated with the mixedness of a state and the probability distribution which comes from the fact that any pure state can be decomposed according to the superposition principle?
Probability distribution, just one more again.
One probability distribution comes from the fact that a state is mixed, right? And some different kind of probability distribution comes from superposition.
I see.
What's the difference?
I see. I should try it again on the desk. Yeah. Or maybe I will answer you like this. You see, depends which device you have. Yeah. For example, if you have photo counter, yeah, and you have your state something like this, 0 plus something, okay, C0 plus this plus C2, 2, yeah. And you have other way around, your density operator, which looking like this, 0 square, C1 square, C2 square, here is 0 and 0 of diagonal terms, yeah? If you have a photo counter, you have no. So you simply do not see superposition. You need another measurement device in order to see this superposition. You see? So your P of n, in order to see it, should not commute in this case. Yeah, your state. Your P of m should not commute with photon number operator, because now all P of m elements in photo counting experiment they commute with n, with photon number operator. If you do another experiment, so-called phase-sensitive experiment, for example, balanced homodiene detection. This is measuring like this. I have shown this, field quadrature. In this case, this will be sensitive to this one. Because when you construct everything, yeah, you will see clear difference between these states and these states. Because will be sensitive to off-diagonal terms, or what is the same is 1. Okay?
Okay, other questions? So no questions more. So we ask our professor 40 minutes.
Yeah.
So it's very interesting discussion. So if we do not have question, we can have a break. And at 2 o'clock, we have a lunch.
And
I can ask a chaotic question. Like this is
yes,
like
please.
Because like this is related to this discussion, and I don't expect the answer to this, but I was like talking about the measurement and about the coherence of the like density function. I was always wondering if if the process of spontaneous emission can be counted as some sort of like primitive measurement, as after the spontaneous emission, we usually have in a mixed state, not the quantum state. But yeah, this is just what I was.
After spontaneous emission, we may have different quantum states. Actually, it depends on characteristic of the spontaneous emission, because it can be organized in different way. Spontaneous emission, yeah, and yeah, of course, okay, we can measure it, and this is actually done. Yeah.
No, it's not about. I mean, no, this is more. I'll discuss this with you a little bit later. I'll explain what I mean.
Okay,
Right, yeah.
okay, okay. I see.
Okay. So, dear colleagues, let's stop with this, and now we have a break.